The eternal cores. What happens to dead stars in the deep future? The universe we know is dominated by stars in various stages of life and death. But what remains when those stars exhaust their fuel? The answer lies in the fate of white dwarfs, the dense, fading cores of sun-like stars. These stellar remnants, though often overlooked, will ultimately inherit the universe as other stars die out. Their story isn't one of swift destruction, but of an unimaginably slow decay stretching across trillions of years. The long, cold life of a white dwarfs aren't supported by nuclear fusion like active stars. Instead, they resist gravitational collapse through electron degeneracy pressure, a quantum mechanical effect where electrons are packed so tightly they refuse to be squeezed further. This allows them to exist for an astonishingly long time, cooling slowly over eons. The coldest known white dwarf, PSRJ 2222-137b, is 11 billion years old, yet still glows at 3,000 kelvins, comparable to a warm incandescent bulb. From white dwarf to black dwarf, an unseen transition over roughly 10 trillion years, a white dwarf will radiate away its remaining heat, eventually becoming a black dwarf, a cold, dark remnant invisible in almost all wavelengths of light. Currently, no black dwarfs exist in our universe. The cosmos simply hasn't been around long enough for the process to complete. It will take 1,000 times the current age of the universe for the first one to emerge. The ultimate fate? Evaporation and decay, but even black dwarfs aren't truly eternal. Two theoretical processes suggest their eventual demise. The first involves space-time curvature-induced pair production. In regions of intense gravity, quantum particles can spontaneously pop into existence, borrowing energy from the black dwarf itself. Over timescales of 1078 years, this could lead to its complete evaporation. The second, more violent possibility is pycnonuclear decay. Packed so tightly, nuclei within the black dwarf could randomly fuse through quantum chance, destabilizing its structure. In a fraction of cases, this could trigger a catastrophic collapse and a final supernova detonation, leaving behind nothing but radiation. A distant legacy, these events are so far removed from our present that they remain largely theoretical. The first pycnonuclear supernovae are estimated to occur between 101,100 and 1,032,000 years from now. But as the universe ages, these decaying black dwarfs will become the dominant source of light and energy, long after all other stars have faded. In the unimaginably distant future, the universe will be populated by the ghostly remnants of dead stars, slowly dissolving into darkness. The fate of white dwarfs is a reminder that even the most stable objects in the cosmos are not immune to the relentless march of time.